Okay, let's move on then and talk about thermodynamics. So, we need thermodynamic data for a number of reasons, but these are the two main ones. We need to be able to determine the heat release in a combustion process. So we need the heat release from every one of the chemical reactions that are present in our mechanism. So we need the enthalpy of reaction. And we need heat capacities to be able to go from enthalpies at one temperature to enthalpies at another temperature, as we'll see. We also need to be able to calculate the equilibrium constant for a reaction in order to determine the reverse rate coefficient from the forward rate coefficient. And the thermodynamic data allow us to ensure that those forward and reverse rate coefficients are compatible. They're compatible with the thermodynamic data. And as we've said, those of you who use ChemKin will have come across the fact that you need a thermodynamic database to go with your kinetic database, and that's there to calculate these reverse rate coefficients. So this lecture considers classical thermodynamics and statistical mechanics very, very, very briefly. We'll look at sources of thermodynamic data, at the measurement of enthalpies of formation for radicals. That's obviously central to a combustion model or combustion thermodynamic database, but radicals are more difficult to deal with than stable molecules. We'll look at what are called active thermochemical tables, which are in many ways revolutionizing the thermodynamics of our subject, and at the representation of thermodynamic data for combustion models. Okay, so here's a bit of classical thermodynamics. So a constant pressure, then the change in enthalpy is equal to the change in energy U plus P times delta V. So that's one important relationship, because we need to be able to move from energies to enthalpies and understand what we're doing. Delta RH is the enthalpy of reaction. And that's equal to the sum of the enthalpies of formation of the products multiplied by these stoichiometric coefficients that we talked about a couple of lectures ago, minus the same quantity for the reactants. And this is a statement of what's called Hess's law, or if you like, of the first law of thermodynamics. If we know the enthalpy of reaction at a given temperature, then we can work out the enthalpy at another temperature using something that's called Kirchhoff's law, which in integral form is like this. We integrate from temperature 1 to temperature 2 of the sum of the stoichiometric coefficients for all of the species multiplied by their heat capacities under constant pressure conditions. And in this equation here, we're writing down the stoichiometric coefficients for the products as positive and for the reactants as negative. So if we know the heat capacities, we can use this equation to move between enthalpies of reaction at different temperatures. And then we've talked about this before. A constant temperature, delta G is equal to delta H minus T delta S. RT log K is minus delta G, and K is equal to these ratio of these products. What I've omitted here, and this is reprehensible, is that this equation here should really have a standard sign on here. Okay, let's define the enthalpy of formation, because this is what's tabulated. One of the things that we could do is we could tabulate enthalpies of all the reactions we need to know about, but that would be impossibly inefficient. And so enthalpies of formation are a very efficient way of doing those tabulations. And so the standard enthalpy change of formation, which is given the symbol delta FH with this standard sign, which indicates 1 bar pressure. Standard enthalpy change when 1 mole of a substance is formed from its elements in their reference states at a stated temperature, usually 298 K. The reference state is the most stable state at that temperature and at a pressure of 1 bar. So here's an example. The enthalpy of formation of methane at 298 K, it's a gas under those conditions. So we have carbon, so we have the elements, these are the elements in their most stable states at 1 bar and 298 K. Carbon, solid, hydrogen gas, molecular hydrogen gas. And carbon solid here refers to graphite, not to diamond, refers to graphite because just about that's the more stable form under these reference conditions. Obviously, the standard enthalpies of formation of carbon in its reference state and hydrogen gas are both 0. You can also get tabulations of standard entropies. And standard entropies are usually based on the third law of thermodynamics. And so just let's explain a little bit about the third law of thermodynamics. So if you use statistical mechanics, then the basic equation is this, where for a mole, so this is the molar entropy, this would be the Avogadro number. That's the Boltzmann constant. So together these form R, the gas constant. And this is called the number of microstates. So this is the number of ways, one way of thinking about this. There are several ways of thinking about the number of microstates, but the easiest way is to think about the ways in which you can arrange the molecules throughout the energy levels. As the temperature goes up, then the number of microstates is going to go up because there are more ways of arranging those molecules throughout the energy levels. Supposing we have a look at say, the OH radical, yet again. The OH radical has many vibrational states and rotational states. But at 0 K, so at 0 K, all of the molecules will be sitting in the lowest energy level. Okay? They've got no thermal energy at all, so they must be in the lowest energy level, the lowest rotational energy level, the lowest vibrational energy level. So this is called the 0-point level. And there's only one way in which you can put all of the molecules in the lowest energy level. That's by putting all of the molecules in the lowest energy level. So W is 1. So under these conditions, W is equal to 1, and so S is equal to 0. And so that's the basis of what's called the third law of thermodynamics. That because of the thermal distribution of the molecules throughout the energy levels, they're all going to be sitting in that lowest level, and the entropy is going to be 0. There can be something called residual entropy, and this can occur with carbon monoxide, for example. When carbon monoxide freezes down and forms a solid, then the thermal energy is sufficient that the distribution of molecules between the two possible arrangements, CO has got a dipole moment, but a very small dipole moment, and so it can be arranged like this or like this. And that's going to be the lower energy state, But the difference in energy between this and this when CO freezes is quite small. And so you don't get all of the molecules arranged like this. You get some of them arranged like that. So you have, with CO, you can have you have something that's called a residual entropy. Okay, so that's the basis of this form of tabulating entropies, based on the third law of thermodynamics, that the entropy of a perfectly crystalline material at T equals 0 is 0. For some molecules, there is a residual entropy which we need to worry about. And the standard molar entropy, SM standard, is the entropy of 1 mole of a substance in its standard state based on the third law. And just let's demonstrate. There's a little picture up there which shows what's going on, but just let's demonstrate what's going on. The entropy is defined in terms of an equation. ds is equal to dq reversible over t. So what we're doing is so it's important that this change is carried out reversibly, but that is a detail that needn't worry us at the moment. What we're doing is we're changing the temperature slightly by an amount dt, and so this, under constant pressure conditions, is going to be equal to Cp dt over t. And so we can integrate the entropy between 0 and t, and that corresponds to integrating Cp dt over t between 0 and t. We have to, there are going to be phase changes. So if we think about something like nitrogen, then at 0 Kelvin, nitrogen is a solid. It then becomes a liquid. It then becomes a gas. And so we have to go through these various phase changes as well. And the entropy change at a phase change is the latent heat divided by the temperature of that phase change. So for example, at the boiling point, it's the latent heat of boiling, the enthalpy change of boiling, divided by the boiling point. So we have to include those as well. But basically, we're taking equations of this sort based on heat capacities and then integrating up to the temperature they're interested in. And these tabulations usually take place at 298K. So if you look at a thermodynamic database, then you'll find the entropies given at 298K, usually based on this third law basis. Statistical mechanics is a way in which we can use the properties of the molecules to calculate thermodynamic properties. So and by the properties of the molecules, I mean the distribution of their energy levels, which in turn is based upon the rotational constants, the vibrational frequencies, etc. And if you want to see a detailed exposition of this, then just look at Professor Hansen's notes from earlier on this week. But we go back to this definition of the partition function that we talked about a couple of days ago. And the energy is equal to U at temperature T minus U at temperature 0 is equal to nkt squared times d log Q by dt at constant V. So we simply take the logarithm of the partition function and differentiate it with respect to temperature under constant volume conditions, and that gives us the energy, or the energy difference between temperature T and temperature 0. This, in many ways, is the most important, one of the two most important equations on this slide. this is one of the best ways of determining the entropy. Because the spectroscopic parameters, the rotational constants, the vibrational frequencies, especially for stable molecules, are very well known, then we can get very accurate entropies by using this equation here, which depends on ut minus u naught divided by temperature plus nk, and this would, for molar quantities, this will be the Avogadro number, into log q minus log n factorial. And it's much, much better using this approach, certainly for smaller molecules, than using the integral approach, the experimental approach that I showed over here. This is less useful for energies because of this term here. U0 is equal to n E0. So different molecules have got different zero energies. They have different stabilities. And so we usually have to have recourse to experiment to determine energies and enthalpies of reaction based on energies and enthalpies of formation. But the entropy we can use directly, and this is a very, very useful equation. We can also determine heat capacities in the same sort of way, again, with really quite high precision. I showed you this slide before. I still haven't corrected this. This should be I subscript B. And so these are the various expressions for the various types of motion: translation, rotation, vibration, electronic. And we talked about the relationship between these moments of inertia, IA, I subscript B, IC, and the rotational constants that you get directly from spectroscopy. And similarly, these vibrational frequencies here you get directly from spectroscopy, and the disposition of the different electronic energy levels, we gave it OH as an example, again you can get from spectroscopy. So these expressions allow entropies and heat capacities to be calculated accurately from spectroscopic data. It's useful to know where to go to get thermodynamic data. And one place to go is the NIST Webbook. The NIST Webbook is a good, in principle, a good source of information. And so this is methane in the gas phase. And so these are, unfortunately, I haven't put the label here, but these are, this is the enthalpy of formation, and these are in kilojoules per mole, and this is the source of the information. And this is an alternative value with a more recent determination. And this is the entropy. You can see reasonably high precision from calculation. But you can probably do a better job than this now. And below it, you can also see the vibrational frequencies. So there's a tabulation of the vibrational frequencies here. Now, especially when you go to radicals, the Webbook itself can be really quite out of date. So the NIST values are sometimes not very reliable. But what you can do on the same website is you can go to this Computational Chemistry Comparison and Benchmark database. And I'll show you this in just a second. And so this contains links to experimental and computational thermochemical data. The key thing is the experimental data for the time being at any rate. For a selected set of 1,272 gas phase atoms and molecules, but they're all fairly small. So they're mostly atoms with atomic numbers less than 18, although there are some heavier ones as well, and with 6 or fewer heavy atoms and 20 or fewer total atoms. And they contain these things: atomization energies, which I'll define in a minute, vibration frequencies, bond lengths, bond angles, rotational constants, experimental barriers to internal rotation. It's a phenomenal source of information. Okay, just let's see if I can get this. So let's maybe look at C2H5. So C2H5, and we want gas phase data and thermodynamic data, and we also want, let's look for infrared spectroscopic data. We can search it, and here's C2H5. Okay, and so there's the value, 119 plus or minus 2, a review by Wing Sang. And then and references to those data. But on this page, in addition, if you look under data at other public NIST sites, there's this computational chemistry comparison and benchmark database. So we can click on that. And here's a list of enthalpies, energies, atomization enthalpies, et cetera, from both experiment and from theory. And so if we click on the experiment there, then we get what is probably a better determination of the enthalpy of formation of C2H5. It actually comes from a slightly older review by Berkhout that I'll refer to later on. But it gives you the enthalpy at 120.9 and 131.8. Sorry, it gives you the enthalpy at 298K and also at 0K. And it also gives you the entropy. And it gives you uncertainties. And for many species, that's a good way of doing it. So just let's go back and just let's have a look at OH, which I'll talk about. Whoops. In a little while. So there's the hydroxyl radical that we're interested in. Okay, and the hydroxyl radical is given from a review from 1998. And as you'll see, that's not a reliable source of information, but that's still on the NIST website. If we go to this computational chemistry and comparison and benchmark database, which is too much of a mouthful, then we find a value here, 37.36, which comes from a review, which again I'll refer to later on by Rusic and colleagues from 2006. And the value has changed significantly within the uncertainty. So the uncertainty is very small, 0.13 kilojoules per mole, and the value for OH has changed quite a bit from that value from 1998. So I would recommend that you use this NIST database, but with a health warning, and certainly check this CCC, etc. database, because that's a good way of looking up information. Okay, so this is information taken from that database for CH3. Sorry, I hadn't labeled that this was CH3 in the slide, so that's why that yellow slide is there. And this is comparing calculated and experimental vibrational frequencies for the methyl radical. Sorry?
Oh, this is kind of a question. So if you know that this number is wrong in this, why doesn't it just get updated?
I don't know. The updating databases is a problem. There presumably isn't money at NIST to do it. And DOE is now funding these active thermochemical tables. And so I'll refer to those in a minute, and that's a much more useful database, but it's much more difficult to access. So, there are problems with this. But yes, it doesn't get updated and hasn't done for many years. Okay, so these are calculations at this level that using this density functional theory with these. The theoreticians among you will know what this stuff means. The rest of you don't need to worry. But what is interesting here is just how difficult theory finds it to determine, for example, the umbrella mode. Methyl, as we said yesterday, is a planar molecule, and so there is an umbrella motion where the H's move up in and out of the plane. So you can imagine opening and closing an umbrella and actually going past the point of the planar point with the umbrella. This level of calculation gives 523 wave numbers. The experimental value is 606 wave numbers. And this is the lowest frequency vibration in methyl, and it turns out to be very important in determining the entropy of the methyl radical and the densities of states of methyl in reactive systems. So there are some issues associated with using theory. If you're dealing, this is a lower level of theory. If you're dealing with stable molecules such as methane, then the agreement is somewhat better. But it's with these radical systems, and especially the low frequency vibrations, that there are problems. Now, what about radicals? If you're interested in the enthalpy of formation of say, heptane, the way you would do this is by burning the heptane and looking at the enthalpy of combustion. And you would then convert that enthalpy of combustion into an enthalpy of formation because it will produce CO2 and water, and we know the enthalpies of CO2 and water. So we work out the enthalpy of reaction, and then knowing the enthalpy of formation of the products, we can get the enthalpy of formation of the reactants. But with radicals, you can't do that. It's difficult to put radicals inside a bomb calorimeter. And so we have to use different methodologies. And so this is a discussion of some of them. And an important paper is this IUPAC review, the evaluation of thermodynamic data for radicals, published in 2005 in the Journal of Physical and Chemical Reference Data. It covers a relatively small number of radicals, but it is a definitive statement. Some of these have been somewhat updated since then, but by and large, it's a pretty good statement of those radical heats of formation. Let's have a look at an example at CH3. And these are the references that are given in this Rusich review using kinetics, photoionization spectroscopy, and electronic structure calculations. So high-level electronic structure calculations these are high-level calculations, for a small species like CH3 can give you good values for the enthalpy of formation. And the recommended value is 146.7 plus or minus 0.3 kilojoules per mole. So really very accurately determined. And you can see, one of the things that I said yesterday was that by and large, it's difficult to do much better than 4 kilojoules per mole, certainly for transition states, but even for ground state radical energies, using relatively run-of-the-mill electronic structure calculations. And so to be able for electronic structure calculations to contribute to this process, they have to be very high level, because we're dealing with really quite precise determinations of these enthalpies of formation. Okay, so here are a couple of examples of kinetics. And so this is work done in the Catholic University in the early 1990s. And what they're doing here is looking at two reactions, R plus HI forming RH plus I, or it could be BR, and the reverse reaction. And so they measure the forward rate coefficient and the reverse rate coefficient, and that's equal to the equilibrium constant. And then what they can do is they can say, okay, well, RT log K is equal to minus delta G, which is equal to delta H minus T delta S. So basically, you've measured this using this kinetic determination. You can calculate this using statistical mechanics, as we discussed earlier on. And that enables you then to determine this. And what we should be doing, what I should have been doing, is putting R's in here, because these are Gibbs energies, enthalpies, and entropies of reaction. So this then enables you to determine the enthalpy of reaction at a particular temperature. And then we can convert that to the enthalpy of reaction at 298 K using that expression I showed you earlier on, where you can go from the enthalpy at one temperature to the enthalpy at another temperature using the heat capacities. And so then from that enthalpy of reaction, we can go to the enthalpy of formation for the radical, because we know the enthalpies of formation of RH, of HI, and of I. So we know all of these, and so from the enthalpy of reaction, we can find out the enthalpy of formation of this radical R. And this was done quite extensively by the group at Catholic University, generating enthalpies for many of these radicals here. Another way of doing it is to look at the reaction under equilibrating conditions. And so we've got H plus C2H4 forming C2H5. And C2H5, so this is generating H by pulse photolysis, allowing it to react with ethylene and form this ethyl radical. The ethyl radical at low temperatures will be stable, but at higher temperatures, it can dissociate back to form H plus C2H4. This is the time dependence of the hydrogen atom at low temperatures, where this reverse dissociation doesn't occur. If you go up to temperatures of something like 800 K, then you get this different profile here, where what is happening is H plus C2H4 and C2H5 are equilibrating, and then there's a slow loss of that equilibrated system. But by analyzing those data, you can get the forward rate coefficient, the reverse rate coefficient, and the equilibrium constant, and then go through this same sort of analysis here. Those are kinetic measurements. You can use photoionization spectroscopy in the following way. So this is a paper by Rusic. And what you can do is you can look, sorry, that R2 should be somewhere over here. You can look at the ionization of the methyl radical here. So this is sorry, these two are moving in different no, they're not moving in different directions. This is increasing energy in this direction, decreasing wavelength, and you're photoionizing the methyl radical and changing the and you're studying this by changing the frequency of the radiation, or the wavelength of the radiation. And you can see that at long wavelengths, nothing happens. And then you see this signal which comes from methyl plus. And from the analysis of this profile, you can get the threshold for this ionization process here. You can do the same thing for methane, except now this is dissociative ionization. So you're looking again for the methyl radical as you increase the photon energy. And when you see the methyl radical, then what's happened is when you see the ion of methyl, then what has happened is this process here where it's dissociatively formed the ion plus the hydrogen atom plus an electron here. And if you take one minus the other, then that corresponds to CH4 going to CH3 plus H. And so you get the enthalpy of reaction for that, and hence, knowing the enthalpy of formation of CH4 and H, you can get the enthalpy of formation of the methyl radical. This, if you're interested or need to use enthalpies of formation of, of radicals, this is the Berkhout paper that I mentioned earlier on. And he tabulates things in terms of bond enthalpy changes or bond energy changes. And these are the definitions of those. But this is a good route to enthalpies of reaction and enthalpies of formation. And so a paper that I would strongly recommend. And it's 1994, so that's nearly 20 years ago. But for some of the larger radicals, not a lot has changed in that time. Now, thermodynamic databases, we've talked about NIST. Now, this is a much more modern approach to these sorts of databases. So it's called Active Thermochemical Tables, and it's developed at Argonne National Lab using both experimental and theoretical data, and it's been led by Branko Rusic. There is also another network which is based exclusively on very high-level calculations developed by Attila Cezar in Budapest, and there's a reference to it there. And that's a smaller database, but it's easier to access. Okay, what's the basis? The basis is shown here in outline. Supposing what we're doing is we want to know the enthalpy of formation of CO2. We need to, that's the actual value. That's the reaction that's involved. And so we could determine that energy there directly and experimentally. So that involves the complete oxidation of solid carbon, of graphite, with oxygen, forming CO2 in the gas phase. Or we could do it in two stages. We could go to CO plus oxygen, and then we could oxidize the CO. And those two routes must be compatible. This is a reflection of the first law of thermodynamics, which says if you go around this cycle here, let's go down here and then go back in the reverse here, then you get back to the same starting point, and the total enthalpy change in that cycle must be 0. That's the first law of thermodynamics. So if we look at it in another direction, this must be equal to the sum of those. Of course, there are experimental errors in both determinations, but by using the two of them together, you can get a more precise value for the enthalpy of formation of CO2, and also a reduced uncertainty in its value. And so if we go, so that's the basis. And so if you look, so here's H and O, so lots of systems involving H and O, and there are lots of reactions connecting them, involving both radicals and ions, and there must be compatibility between all of these. Again, there is an uncertainty in each of the measurements, but what you can do is take them together, analyze them together, and get an optimal value and an optimal value for the uncertainty in the formation of any of the species that you're interested in. So this is a small subsection of the argon thermochemical network. At the time that this slide was prepared, there were 600 of these primary what they call primary vertices and 3,200 secondary vertices, so basically what that's saying is there were very, very many determinations in this overall system. And so this is a section of the way in which the analysis is done. This is a little bit of it here where we've got this reaction, H2 plus a half O2 going to water. And so this column here defines that reaction in terms of reactants and products. And here are the measurements, independent measurements with uncertainties. And then you get other determinations throughout this overall matrix involving different species. And what they then do is to optimize that whole matrix. And if a new determination comes along, then they re-optimize. And that's why it's called an active thermochemical database. And here are some examples of crucial species where there have been significant changes in, well, the first one, there is a significant change in the enthalpy of formation. So this is the hydroxyl radical, OH, a simple diatomic molecule. And people as old as me happily accepted these determinations here, which were spectroscopic determinations. Richard Barrow was a colleague at Oxford, and I believed implicitly anything that he did. But the methodology was really very good. But it turns out that it wasn't quite good enough. And so these are the values that came out of the spectroscopic measurements. These are the JANAF tables, which is a big tabulation of thermodynamic data. Values for the enthalpy of formation at 0 Kelvin, which are slightly over 9 kcal per mole. And these are the recommended values using current experiments and also calculations. And it's changed by something like 0.3, 0.4 of a kilocalorie per mole. But the uncertainty is very much reduced as well, compared with these values here. This uncertainty here was not a very good determination of the uncertainty. So the enthalpy of formation of the OH radical has changed significantly. And that was why I showed you the value from the NIST database, because that is still recommending the old value. So you have to be careful. You have to know what you're doing. And this is problematic. So this shows you the JANAF value with its uncertainty and the current value from ATCT, or the then value from ATCT, with its uncertainty. Similar situation, I don't really have time to go through the details, for the HO2 radical. And so this again is, this is the JANAF recommended value with its uncertainties. And in red here is the ATCT value with its uncertainty. And that comes from primarily, those changes come primarily from recent careful experimentation associated with calculation. So this is a whole set of values. You can see the differences in the values for HO2. And this is the current recommendation from ATCT. The changes are, well, there was a lot of variation in the early days. Interesting recommendation by Benson here, which really helped to change the way in which we thought about the HO2 radical. But this is the latest recommendation, 2.94 plus or minus 0.06 kilojoules per mole. Really very incredibly precise. Sorry, that's kcal per mole. Okay, here's an interesting example of the way in which things are now. So this is this reaction here, triplet CH2 plus H going to CH plus H2. And I looked into this about a year ago because I was doing some work on interstellar chemistry. And interstellar chemistry occurs at incredibly low temperatures of the order of 10 Kelvin. There were some reactions where it would have been helpful to be able to use thermodynamic calculations. And so this is triplet CH2, so this is the triplet state of CH2 reacting with H, forming CH plus H2. And these, interestingly, these reactions occur, these are quite important in interstellar media. And so I got in touch with Branko Rusic to ask him what his latest best values were. And he used what are called these, where's the definition? Total atomization energies, TAE0. So that's taking CH2 and converting it into carbon and hydrogen. And taking CH and converting that into carbon and hydrogen. And those values can be calculated with high-level theory very, very accurately. And so with these values, using these values, he was able to recommend a value of, in my money, 14.04 plus or minus 0.35 kilojoules per mole. And then if you look at the latest ATCT value, then it's something like 14.15 plus or minus 0.18 kilojoules per mole. That's the enthalpy of this reaction here. Okay? 14.15 plus or minus 0.18 kilojoules per mole. This is a really difficult species to work with, and these are incredibly precise determinations. But from my point of view, what I wanted to know about was how well can I determine the equilibrium constant at 10 Kelvin. And so if we look at the logarithm of the equilibrium constant, then it's equal to minus delta RH over RT plus delta S over R. And so the uncertainty squared, the variance in log K, is equal to the variance in this enthalpy of reaction, this thing here, divided by RT squared, plus the variance in the entropy of reaction divided by R squared. And the entropy we can determine really very accurately because these are small molecules. The spectroscopy is very well determined. We can use statistical mechanics. And so what we can do then is we can look at this quantity here. We can ignore this because the contribution to the uncertainty is very small. And so what we can do is we can look just at the enthalpy change, and we can say that the uncertainty sigma in log K is going to be equal to the uncertainty in delta RH divided by RT. So we're taking the square roots there because we can ignore the entropy. And if you look at the values of that, Then at 1,000 Kelvin, if you're interested in combustion, then the uncertainty in the equilibrium constant is of the order of 2%. It's minute. That system is as well determined as we would ever need it to be. But if we go to 10 Kelvin, the uncertainty is a factor of 9. So we know that equilibrium constant at 10 Kelvin only to within a factor of about 10. And so that's going, if you've got a rate coefficient in one direction, when you calculate the rate coefficient in the other direction, then it's going to be good to something like a factor of 10. And that's one of the problems of working at these incredibly low temperatures. Even using theory, you've got to use phenomenally high levels of theory if you're going to get results which are going to be of value to you. Okay, just let's quickly finish this off, and then we can break. So this is that other database that I was telling you about, coming from the Budapest group. It's based on a similar basis, and then one of the things I've propagated is doom and gloom about where you look up your thermodynamic data. But it's not, as far as combustion is concerned, it's not desperately bad, because what you can do is you can use these databases provided by Berkhout, and you can access them through this database here. And these are very closely linked to both ChemKin, because this is the source of the data that goes into ChemKin, and also to ATCT. And so the best values from ATCT go into this Berkhout database. So this is a good place to look. And you need to understand what's going on, though, because they use what are called NASA polynomials. And so the heat capacity divided by R is given by this polynomial here, with these parameters A1, A2, A3, A4, A5. The parameters are given, but there's the temperature dependence. Similarly for H over RT and for S over R. And as I said, it's linked to ATCT and also used in ChemKin. And so here's the Berkhout database. This is the entry for CH3. And so the first few lines is information on methyl generally. So sigma equals 6. This is related to something called the symmetry number of CH3, which if you're using statistical mechanics, you need to know something about. These are the moments of inertia. These are the frequencies. Nu are the frequencies. This is the enthalpy of formation at 298K, 146.7, plus or minus 0.3, which is the value that comes from the ATCT. There's the enthalpy of formation at 0 Kelvin. Here's the reference from Rusic. And this is some information on methyl. And then this is information, 200 to 600 is information on the tabulation coming below here. And so these are the values of those A1s to A whatevers. Down here, the first 7 entries are A1 to A7 from 1,000K to 6,000K. So these are the values you would use if you're working in this regime. And the second set are from 200 to 1,000K. And the temperature ranges are specified in here. So it goes from 200 to 1,000 to 6,000. They always have a break at 1,000K. And so if you have data below 1,000K, then there'll be 14 numbers here which correspond to these A1 to A7s. And these are the data that are present in ChemKin that are used to calculate the equilibrium constant and hence to calculate the reverse rate coefficient from the forward rate coefficient. As I said, they're linked directly to ATCT. Okay, I apologize for going on, but we better break there. And if you have general questions that you want to share with everybody, then let's do that in a quarter of an hour. Okay, thanks very much.